Hey, what's up guys? It's Dr. D-Flo, and this project started as a few small upgrades to the DMC2 Mini, a desktop mill I built in a previous video. But one thing led to another, and it turned into what I'd now call one of the most capable, compact CNC machines that you can have in your garage. But before I show you how I got there, let's do a quick tour of the final machine. First stop, the MASSO G3 Touch controller. The stock DMC2 Mini used Mach 3, which is a deprecated software and required a separate laptop to run the mill. This all-in-one controller replaces that clunky setup with a large touchscreen and modern UI. I can't overstate how much of an improvement this is. We'll cover features, wiring, and programming later in the video, but big thanks to MASSO for sending it over with no strings attached. The biggest upgrade in terms of size is the new stand and enclosure. Starting at the top, the windows are 6mm impact-resistant polycarbonate, and opening the front door, you can see the safety interlock switch at the top. If the door opens while the machine's running, the program pauses and the spindle stops. I built this machine for my class, so common sense safety measures were a must. Of course, inside the enclosure, we have the DMC2 Mini from Sheriff. I've stripped off a few components, but this is more or less the base machine, and it's a solid starting point. The steel frame and linear rails give you a surprisingly rigid platform for such a small mill. As you probably noticed, there's a new spindle, the Spinogy X22. While it shares nearly the same form factor as the outgoing one, it has several major upgrades. It spins up to 30,000 RPM, that's 6,000 more than before. And it's significantly quieter thanks to water cooling. Most importantly, it supports pneumatic tool changes, so swapping cutters is fast and easy. I'm just one step away from a fully automatic tool changer, and that upgrade's coming soon, so hit subscribe to catch it. I'm fortunate that Spinogy provided the spindle in exchange for being featured in this video. One of my favorite parts of the original DMC2 Mini was the flood coolant system. It gives you a noticeably better surface finish without needing to run an air compressor like MIST systems do. But the old enclosure leaked and quickly filled with chips in hard to reach areas, so I wanted to fix that. The metal shavings from the new spindle now fall into a custom fabricated stand, which features a sloped basin that funnels chips into a drawer. To help prevent sticky chips to make their way down to the bin, there's even a washdown mode. A tube on the side sprays coolant out of it. If I pull out the chip drawer, you can see how spacious it is. A fine mesh catches the shavings while the coolant drains through a flange at the back and returns to the tank. On the opposite side of the stand, there's a tool drawer, of course for tool holders as well as Allen keys. Underneath that is the auxiliary door, where there's the chiller and pneumatics for the spindle. Space is tight in my garage and classroom, so I try to pack in as much functionality per square foot as possible. I'm really excited to walk you through this entire build in one video. If you're interested in a specific upgrade, just use the video chapters to jump around. But first, let's see the whole setup in action, the new controller, the enclosure, and spindle. To kick off the build, I want to walk you through the enclosure in CAD. This model is available on my website, so feel free to explore it in further detail. First, since the DMC2 Mini is a benchtop machine, I didn't want the enclosure to make it feel oversized. To save space, the mill sits off-center to accommodate the X-axis motor, which sticks out on the right. The stand itself is 36 inches tall, including the leveling feet, which puts the mill's table right at bar height, about 42 inches. The total footprint of the enclosure is 28 inches wide and 26.5 inches deep, not including the spindle's control panel hanging off the left. When you're loading new stock or inspecting a part, you often have to lean into the enclosure. It's important that there aren't any exposed buttons or handles that you could bump or get caught on. I made this mistake with the e-stop button on the enclosure for my larger mill a couple years ago. This time, even though the MASSO controller has its own e-stop, I've added a primary e-stop on the front of the enclosure that cuts all power, and it's recessed to prevent accidental presses. Same goes for the drawer handles. They're folded metal, so nothing sticks out. Behind the control buttons, there's a hidden compartment where the wiring and power supplies are housed. You can also access this area by removing the top rear panel. That small frame square at the bottom will be an access port for routing cables. If we peel away the sheet metal, you can see that the frame is built from a mix of 1.5 inch and 1 inch square tube stock. And with that, let's jump into the fabrication. So I've got the plasma table loaded up with a 16 gauge sheet of mild steel. I'm cutting out all the flat components, the outer panels, and the tab and slot parts for the basin. I don't have a metal brake in the shop, so I'll come back later to how I handle the drawers and doors. Here are the finished plasma cut parts alongside the square tubing. To keep everything fixtured for welding, I'm using a 48 inch by 30 inch Rhino cart. No sponsorship or anything, but it's great for small parts. That said, as soon as you start building anything furniture sized, the 30-inch width becomes a problem. So I picked up the expansion kit to stretch it another 12 inches, and that's been a game changer. With the larger surface, I can finally clamp all the way around the perimeter of the frame. That's been crucial to keeping things square and minimizing warping. Honestly, I'm learning that the secret to welding is buying clamps, realizing you don't have enough, and then buying more clamps until you run out of money. With everything squared up, I tacked on the base sheet metal and started welding in the supports for the hidden electronics compartment. Next up is the basin, a 6-piece assembly with long seams that all need to be watertight. This is going to be a lot of welding. Now I can add the rails for the drawer slides. I used my mill ahead of time to drill the mounting patterns before welding these in place. That should save time later and help with accuracy. And finally, I'm attaching the 2 cross beams that the mill will sit on. I'm using the base components of the DMC2 Mini to space them correctly. With the internals done, I can flip the stand over and weld on corner plates for the leveling feet. With the frame complete, let's talk about the drawers, doors, and front panels. As I mentioned earlier, I don't have a metal brake, so I had to outsource these parts to a third-party bending service. Here's where I ran into a problem. I started looking for bending options after I'd already built the stand. That meant I couldn't really change the design. I needed the sheet metal to match what I had in CAD. What I didn't realize is that the long, narrow shape of the chip drawer makes it tricky to bend. Most services either couldn't do it or required a custom quote, except one. Oshcut could handle it with no special setup. Now, I'd already blown most of my budget on the welding table extension and clamps, so I reached out to Oshcut to see if they'd be willing to help out. Not only did they say yes, but they even sent over footage of the parts being bent, which was very cool to see. As part of that collaboration, I promised I'd walk you through how easy their online service is to use. And honestly, this could help you too, especially if you want to build this enclosure without a plasma table and/or metal bender. I'll walk you through submitting the drawer design. Here's the component in CAD. From here, I can flatten it and export a DXF file. If you want 50% off your first order, head over to app.oshcut.com/Dr. D-Flo and sign up. Once you're logged in, you can upload your DXF file into their online configurator. The first step is to pick your material and thickness. This needs to match your CAD model since bend radii and offsets depend on it. I chose HRPO steel, which is hot rolled steel that takes an acid bath to remove its mill scale, which is much easier to weld and paint. A DXF file only contains lines, so in the configurator, you will assign each line as either a bend or a cut. It's really straightforward. My favorite part is the real-time bend simulation. It'll warn you if there's a tooling collision, and it highlights exactly what needs to be changed. No errors this time, but some of the bends were definitely close. Whether you're building this enclosure or working on your own project, check out Oshcut using my affiliate link. Their platform makes metal fab surprisingly accessible. Here you can see all the parts that Oshcut sent out, including brackets for the top aluminum extrusion enclosure. But my favorite component is the drawer handles. Look at how narrow that clearance is for the bend. I need to make the chip drawers watertight, so I'm welding up the corners. To avoid blowing through the gaps, I'm backing the weld with a small piece of angle iron. Obviously the drawer is less likely to leak since I only have to weld the 4 shortest edges. That brings me to my latest boondoggle. The access door for the coolant reservoir is 9 inches wide, but most of the common 3-gallon coolant pump kits come with tanks that are 11 to 13 inches wide, so they don't fit. I knew this was going to be a problem somewhere in the back of my mind, but I was hoping I'd find a narrow metal pan that was under 9 inches wide and could still hold about 3 gallons. No luck, and like with the chip drawer, I couldn't use Oshcut because the wall height would be too tall and collide with the bending tools. So a bit desperate, I framed a custom tank using 1-inch tube stock and welded sheet metal to the outside. That gave me long continuous welds, which had to be perfect to hold coolant. It worked, but it was a pain and it's heavy. For the fabricators out there, if you've had to solve something like this, how would you have approached it? Finally, it's time for paint. I'm using a 2-part epoxy spray for the stand and basin. Epoxy is a great choice here. It resists scratches from metal chips and holds up well to coolant since it's chemically inert. In between helping with the stand, Andy was busy building the second DMC2 Mini that Sheriff sent out. She is a beast, and I'm very grateful for her help. We're building a second machine for two reasons. First, I'll need multiple mills for my class, and second, I drilled and tapped mounting points for the new X22 spindle and eventually an automatic tool changer. Something that would have required completely disassembling the original machine. That one's already dialed in, so I'd rather not mess with it. The second DMC2 Mini lined up perfectly with the mounting points on the stand. Always a nice moment when that happens. Before moving on, I want to highlight a couple changes that we've made to the machine beyond the extra threaded holes. First, we removed the Y-axis rail and ball screw covers on the front of the machine. Doing this gave us an extra inch or 25 millimeters of travel. Again, this is something I'm experimenting with for the future tool changer setup. Eventually, I'll replace these covers with a flat bellow that spans both Y-axis rails and the ball screw to keep chips out while maintaining that extra travel. The second change is the motors. MASSO sent out their closed-loop stepper motors, which have integrated drives, meaning you don't need a separate drive in your electrical cabinet. All the control logic is built right into the back of the motor. That makes wiring cleaner and simplifies your overall setup. It also solves a minor annoyance with the stock setup, those bulky DBs that do not fit in the wire looms. In terms of performance, these MASSO motors have the same torque as the stock motors, so if you already have working motors, this upgrade probably isn't necessary, but if you're starting fresh, they're a great option for their simplicity. Last video, I made a custom bracket for the X-axis motor, which was stiffer than the one that came with the mill. However, I found out later that there is a standard mounting block for 1204 ball screws called the HM1057. It's honestly cheaper than buying the aluminum to make a second mount, so I'm gonna go ahead and give it a go. The final change, for now, is the addition of MASSO's optical in-stop switches. These are plug and play with the controller. This is another reason why I can't leave the Y-axis completely exposed. I'll need to make sure the optical path isn't accidentally blocked by a stray chip, which is why the flat bellow I mentioned earlier will be important. Next, it's time to get everything wired up. Since the new spindle requires 220 volts, I've wired everything around that voltage. Quick aside, in the last video, several of you pointed out that if the stock spindle was really 3 horsepower, or about 2.2 kilowatts, how could it run on a 110 volt 20 amp circuit that also powered the rest of the electronics? The likely answer is it couldn't, or at least not continuously. That 3 horsepower rating was probably the peak power, a bit of creative marketing. Realistically, the stock spindle was likely putting out closer to 1.5 to 2 horsepower under normal conditions, but there's no documentation to confirm this. I should see a noticeable improvement in performance with the X22, which delivers a true 2.2 kilowatts of continuous power at its max 30,000 RPM. Now back to the wiring. The incoming 220 volt line first runs through this breaker and then into a 24 volt power supply. That 24 volts is used to activate this AC contactor, but only when the E-stop is not pressed. So the E-stop cuts power to the entire system by opening the contactor. Once the contactor is closed, mains power flows to 2 separate power supplies. One is a 36 volt PSU for the stepper motors. That's the maximum voltage supported by the MASSO closed loop steppers. The other is a 12 volt supply that runs the coolant pump, washdown solenoid, LEDs, and other accessories. Let's move on to the brains behind the operation. To my knowledge, the MASSO G3 Touch is the only all-in-one controller that can be used for nearly any subtractive technique, from plasma to 5-axis machining. When I say all-in-one, I mean the screen also acts as the computer and contains the breakout board for connecting all the hardware. You do not need to buy a separate desktop or leave your laptop connected by USB while it's running. G-code files can be uploaded via USB or wirelessly. The breakout board has 24 inputs and 18 outputs, not including step and direction signals for 5 discrete axes and analog spindle control. On the software side, these inputs and outputs can be quickly mapped to handle common functions such as actuating a drawbar during an automatic tool change for milling or responding to changes in arc voltages for plasma cutting. Now I know I just said that you can wire all of your control signals directly to the back of the touchscreen, but that means running individual wires up to the control arm, which pivots and tilts. This extension module, which plugs into the back of the G3 Touch, and its daughter board, which is connected through these DB connectors, allow us to relocate all of those connections inside of the stand of the mill. Now there's only 2 DB cables running between the extension module and the screen. These cables are easy to swap out if they get snagged. MASSO's documentation is beginner friendly, and I will also have wiring diagrams on my website showing how everything is hooked up. I'll include one for the full upgrade with all the new components, as well as a simpler version if you're just replacing the stock controller with the MASSO Touch. But let's get back to the electronics tray. These separate terminals right here are for routing the wiring to the stepper motors. Since the MASSO steppers have built-in drives on the back, I'm running an 8-conductor cable to each one. That cable carries both power and the usual control signals a drive would expect: step, direction, enable, and alarm status. This leads me to a couple oddities with the MASSO controller. First, the control board does not have a dedicated stepper motor header where you can plug all the signals in right next to each other. Instead, I have to break them out across multiple terminals. You even need a separate relay to control the enable signals if you want the motors to be disabled when the e-stop on the MASSO Touch is engaged. More on this in a second. So I wouldn't describe the MASSO motors as plug and play with the controller, but it is manageable. The second head scratcher is that the 18 outputs are only capable of 5 milliamps, which is not enough current to drive my favorite DIN rail relays, which need 8 milliamps. Forget about directly controlling larger loads, as this 10 amp relay requires 30 milliamps to trigger. Even more problematic, the ES or emergency stop output pin, which is part of the e-stop circuit, has an active voltage of 2.3 volts. When the e-stop button is pressed, this voltage drops to 0. The purpose of this output is to disable the stepper motors, spindle, and other moving machinery. However, most electrical devices do not recognize 2.3 volts as an on signal. The answer to the second problem is just to buy the MASSO relay module, which takes all this into consideration. My last critique is that the main board does not come with internal pull-up resistors. These have to be wired externally. If you're not familiar, pull-up or pull-down resistors are important for reading the state of buttons, as it ties the input pin to a known value when the button is unpressed. All the buttons on my front panel, stepper motor alarm signals, and the door interlock need pull-up resistors. Externally adding them is clunky and poses a risk of shorting the board. Fortunately, if you buy the extension module, there are dip switches to manually activate pull-up resistors on each individual input. But most 3D printer controller boards have pull-up or down resistors that can be activated electronically and have outputs that can source large amounts of current. These would be my suggestions to MASSO on their next version. You can see that I stacked the MASSO relay as well as the PWM controller for the coolant pump on top of the extension board. Let's just say that this wiring is more of a creative expression than an organized one. The last thing I want to mention is the special precautions for probing. As a reminder, the DMC2 Mini uses a touch probe that works by detecting electrical connectivity between itself and the machine frame. But we don't want this signal directly connected to the MASSO controller, because if a stray wire contacts the frame, it could send high voltage straight to the controller and fry it. To prevent that, I'm using an optocoupler and an isolated ground to detect when the probe makes contact. The optocoupler keeps the sensing circuit completely isolated from the controller's logic. Now I can slide the electrical tray into the stand, a tight fit, but it's going according to plan. When I first turn the coolant on, I need to check and make sure none is able to sneak through the welded seams in the basin into this compartment. I'm going to run the wires to the stepper motors and limit switches before powering everything up. These holes in the back are for cable glands to let the wires into the basin, but keep the coolant from leaving it. The screen's on, it's bright, and the viewing angles are great. I'm running version 5.1, which is the latest stable release at the time of filming. It took about 5 minutes to set up the axes. Usually you're stuck digging through configuration files with a text editor, but not here. MASSO makes this process really self-explanatory, which is great if you're just getting started. I'll quickly walk you through how I set up the Y-axis. If you want to configure the other axes or input-output settings, I recommend checking out MASSO's documentation. I'll also include a table on my website that maps each input and output to its function. So at the top of the screen, we're going to click Setup. Here we have two lists. One is the inputs and one's the outputs. The green and the red icons are the state of these input and outputs. If I look at my wiring diagram, I know that the Y-axis limit switch is plugged into pin 20, so I'm going to scroll down the inputs list to pin 20. I'm going to double click. Now the Y home sensor is that top option, but I can go ahead and scroll down this table and you can see all the different functions that this input can be assigned to. We'll go back to the top, we're going to click Y home sensor and then do select. We can see right now that the state of it is low, but if I block the optical path, it switches to high. That is the behavior that the MASSO control is expecting for limit switches, but let's say for some reason when the limit switch is not triggered, it's high, well you can invert the logic by just clicking the space button when the input's highlighted. So now we can see it's low, I click the space, it's high, and again when I block the optical path, that'll go to low. But I'm going to click space again to uninvert it. This screen will be super helpful for debugging. If a sensor isn't acting the way you expect, this is the first place to check. On the left, we've got the machine settings. I'm going to go ahead and double click on Y-axis. Here I can access all the settings, including motor configuration and travel limits. We're using 1204 ball screws, which means the table moves 4 millimeters per full rotation of the screw. So that distance per revolution should be 4 millimeters. Now to get the motor to complete that one rotation, the controller will need to send a certain number of pulses, and that number is determined by the dip switches on the back of the stepper motor. The more pulses per revolution, the smoother and more precise the motion. So why not crank it all the way up to 51,200 steps per rev? Well, here's a trade-off. The MASSO controller maxes out at 110,000 pulses per second. If it takes 51,200 pulses to make one full revolution, our max speed on the Y-axis would be around 8 millimeters per second, or about 18 inches per minute, which is slow. So you've got to balance smoothness with speed. Most modern controllers can output upwards of 1 million steps per second, or support external drives that simulate higher resolution internally. But in this case, that's not available, which honestly is a little surprising. Right now I've got it set up to 4,000 millimeters per minute, about 157 inches per minute, at 6,400 pulses per revolution, which translates to a pulse rate of 107 kilohertz, just under the controller's limit. Most of my cutting happens under 2,000 millimeters per minute, and given the small work envelope, fast travels between cutting moves aren't a huge time saver. But if you're building something bigger, like a large router or plasma table, you may need to dial down your pulses per revolution to hit higher travel speeds. I still need to optimize my acceleration values. 300 millimeters per second squared is a safe value. The maximum travel is 205 millimeters. And the next field is for backlash compensation. In the last video, I mentioned that there was some detectable play in the axes, even with the double nut ball screws. Now I have the chance to compensate for that digitally, but I'll need to take some accurate measurements before entering a value here. And finally, there's a setting to invert motor direction. Useful if jogging in the positive direction moves the axis in the wrong way, which was the case for me. You can see that that invert direction is checked. Now we're ready to home everything. We'll go back to the F2 or the program and MDI screen, home, double tap. You'll notice that on the Z-axis, I'm still using the inductive switch that came with the kit. There just wasn't enough room to fit the MASSO optical switch without losing Z travel. Because the new spindle is longer, there wasn't space to route the Z-probe wire underneath it like before. I had to machine a slot to reroute the wire so it wouldn't interfere with spindle mounting. The spindle's added length also interfered with the magnetic probe mount and the coolant lock line holder. So I drilled new mounting holes to reposition both closer to the edges of the Z-axis. Nice. From here we can go to the jog and probing screen, and without any setup, the hand wheel works, which is awesome. We'll go deeper into the basics of the MASSO control when we run our first operation, but I do want to quickly cover probing. Eventually I'll upgrade to a digitizing probe that mounts in the spindle, but for now I want to revisit the stock probe setup since I've gotten quite a few questions about it. Here you'll be able to see my opto isolator circuit in action. If I touch the tip of the probe to this aluminum piece, the probe lights up. Input number 5 on my control, which is the probe, goes to high. You'll also see the word probe at the top of the screen turn from blue to green when it's triggered. To access the probing features, go to jog in probing, and then click the probe icon. I know that we're still missing proper work holding on the table, but I can do a quick test here to show you if the probe works. Since this probe isn't spindle mounted, accurately picking up edges requires you to manually set the X and Y offsets. Those values go here. I briefly walked through how to calculate them in my last video, and Sheriff DMC has a video on it as well, so I won't repeat the full process here. Hey, quick update from the future. I found that with this off-axis probe, the offset values actually depend on the direction you approach from in X or Y. So probing from the left gives you a different result than probing from the right because of how the probe radius adds or subtracts from the offset. You can absolutely write these different offsets down and change them in the control based on which direction you're coming from. It's just not as automated or foolproof as a centerline probe. I'll reach out to MASSO and see if they can support directional offsets in a future version. We're getting so close to installing the spindle, but first I've sorted out the Y-axis way covers. I 3D printed this perimeter piece that holds the individual covers in the back and a flat bellow in the front. On top, a Saunders Machine Works fixture plate holds everything down securely. It's time to talk about the X22 spindle. But first, let's make sure we're all on the same page about how tool changes usually work on a manual or fixed tool spindle. To swap out an end mill, you typically loosen the collet nut, often with 2 wrenches, remove the tool, and possibly change the ER collet if the new tool has a different shank diameter. Then you reverse the process to install the new cutter. Not only does this take time, but if you're like me, you'll eventually drop the tool into the chip basin and spend 5 minutes digging it out of a pile of swarf. On top of that, the stick out, or how far the tool extends from the collet, will be slightly different each time, which means you have to re-zero your Z-axis for every tool change. This can become a real bottleneck, especially if you're using multiple tools on one setup, for example, roughing with a large end mill and finishing with a smaller one to save time. Now compare that process to an automatic tool change, or ATC spindle, like the X22. With an ATC spindle, each tool is mounted in a dedicated tool holder that locks into a spindle using a pneumatic drawbar. You can preload your most used tools, each one already measured and ready to go, so tool changes are fast and repeatable with no need to re-zero. Of course, ATC spindles come with extra components that make them larger. If you're upgrading an existing machine, you'll need to be careful not to lose too much of your work envelope, especially on a compact machine like the DMC2 Mini. That's what makes the Spinogy X22 so impressive. It's the smallest ATC spindle I could find, and yet it delivers 3 horsepower at up to 30,000 RPM. It's not cheap. This variant runs between $4,000 to $5,000. So yes, it might seem a little crazy to put it on a mill that costs half as much, but especially for high-speed machining, where you're taking small, fast cuts, the accuracy and speed of the spindle become critical. Let's take a closer look at the SK20 tool holder. SK20 uses the same steep 7 to 24 taper as ISO 20, but the pull stud geometry for the X22 is different from typical ISO 20 holders. On the left, here's a genuine Spinogy holder, and on the right is one from another manufacturer. Notice the longer flat silver portion on the genuine pull stud. At a minimum, you'll need Spinogy pull studs on all your holders. At the other end is the clamping nut. Spinogy offers holders with ER16, ER20, or ER25 nuts. Mine are ER20. In addition to the spindle, Spinogy also sent over the supporting hardware needed to get it running. Let's start with the chiller. Spinogy offers both air and liquid-cooled variants of their spindles. I chose water-cooled because it's quieter, and in a compact machine like this, I don't have to deal with long coolant lines. Plus, it should offer better thermal stability. The chiller sits in the bottom left of the enclosure, and there's an always-on fan in the back of the stand to exhaust hot air. Next is the pneumatics cabinet, which includes 2 pairs of pressure regulators and solenoids. One pair controls the drawbar piston for tool clamping and releasing. The other handles the tapered blow-off, which clears chips and debris from the spindle interface before a new tool is inserted. The pneumatics cabinet sits right behind the tool drawer. This is tight, but it's also the reason why the tool drawer doesn't go all the way back. And finally, we have the control cabinet. Inside are the usual suspects: a VFD for spindle speed control, braking resistors to shorten spin down time, and a line filter to clean up the power. The long row of terminals on the bottom is where the chiller, pneumatics, and MASSO controller all come together. This red box is a safety relay. If anything goes wrong, from the spindle stalling to a drop in air pressure that could affect tool clamping, the safety relay will send a signal to shut everything down via the MASSO control system. All these subsystems, the chiller, pneumatics, and control cabinet, could technically be DIY'd, but I'm grateful that Spinogy provided them. Honestly, installing the spindle might be the easiest part of the whole build. All I need to do is plug in a few wires and push some tubing into quick connects. So let's get to it. To keep chips and coolant in and fingers out during cutting, I'm building the enclosure frame from 4040 aluminum extrusion. It's a bit overkill for something like this, but I plan to mount the controller on the side. I don't want any wobble or flex. In previous builds, I've used 2020 extrusions and slid 6mm panels into the channels, but the fit was usually loose and the panels would rattle during cutting. The 4040 channel is wider, which allows for a gasket on either side of the panel to eliminate vibration noise. For the windows, I went with 6mm impact-resistant polycarbonate. Since Oshcut doesn't offer plastics, I ordered these from Cincut Send, another popular on-demand manufacturer. Full disclosure, I originally planned to pay for the polycarbonate myself just to avoid putting 2 competing sponsors in the same video. But Cincut Send insisted on helping with the project, which was a big help because polycarbonate is pricey and I wanted full visibility from all 4 sides of the enclosure. That's especially useful for teaching and of course for filming YouTube videos. Unlike most CAD to part services, Cincut Send offers water jet and router cutting in addition to lasers. They can handle materials like carbon fiber, titanium, and polycarbonate. Definitely check them out if you need to work with something exotic. The visibility for this enclosure is amazing. I'm still trying to figure out what to do with the spindle and the Z-axis wires. I originally designed a pass-through in the bottom of the back window so that the wires come in through there, but I actually do have enough room for them to travel kind of around the top of the enclosure, and this top lip may help support them, keep them out of the way. One item on the to-do list is sealing the gaps where the extrusion meets the stand to prevent coolant leaks. I'll also need to come up with a flap or cover to close off the clearance gap that lets the front door swing freely, otherwise coolant will find its way out there too. For now, I'm going to add the MASSO controller to the side of the enclosure. This VESA mount to 40/40 bracket was cut and bent into shape by Oshcut. Now I can add the light bars to the top and the safety switch to pause the cutting operation if the door is opened. To turn the LEDs on, I need to install the front panel. The first button on the front panel turns on the LEDs, including this digital fabrication sign, which is a nod to the program I teach. Next is the drawbar button for manual tool changes. Check out how smooth it is. With the chiller on and coolant flowing through the spindle, I'll fire it up so you can hear it in action. I've disabled the safety interlock now so the door is open. Here is 10,000 RPM. Here is 20. And here is 30,000. I can easily hold a conversation standing right next to it. Now compare that to my old spindle at 24,000 RPM. It is so loud because the spindle not only rotates the tool, but also a fan on the opposite end to keep the housing cool. It would be very difficult to communicate with my students while this is running. But getting back to the front panel, this blue button, or the third button, is for the coolant. This potentiometer knob right here adjusts the flow rate. Let's trace the coolant path. It exits the nozzle, drains down the basin, and into the chip drawer. A fine mesh filter lets only the coolant return to the reservoir. When the coolant is on, you can press the green button or the fourth button to trigger the washdown mode. This opens up a solenoid allowing coolant from the pump to travel an alternative route to a pipe along the upper left edge of the basin. This pipe has 1mm holes to spray coolant down the basin. The water pressure here is a little low since coolant is still flowing out of the main nozzle. That said, chips from high-speed machining are typically small, so it shouldn't take much to flush them down. If needed, I could always install a second pump dedicated to the washdown line for more pressure. I'm happy to report that there are 0 leaks into the electronics compartment. As for the fifth button, it's currently used to turn off the coolant. MASSO requires that to be a dedicated input, which means I'll need to swap both the coolant on-off buttons from latching to momentary types. Before my first cut, I'm performing final adjustments. The Y direction is nearly perfect, only half a thou or 12 microns of variability across the whole travel. Unfortunately, I wasn't so lucky with the X-axis. I found a 10 thou or 250 micron bow away from the bed. That's significant. For comparison, my first DMC2 Mini only had about 1 thou or 25 microns of variation along the same edge. As several of you pointed out in the last video, this is one of the trade-offs from building precision machines from steel tubing. Machining the surface flat can release internal stresses from the manufacturing process, causing the tube to warp. It's counterintuitive, but you can end up with a flat surface that's no longer straight. The amount of distortion seems to vary. My first machine had very little, but this one wasn't so lucky. Normally I'd ask for a replacement part, but I decided to try shimming the linear rail. My original plan was to build up shim thickness gradually towards the center of the bow, under the assumption that both pieces of tube stock were distorted equally. Of course, nothing's ever that simple. I discovered the top tube was much worse, pushing the top of the spindle forward and skewing the indicator in a way that made me think the bow was away from the bed. After an entire day of fiddling with it, I was able to get the variation down to 2 thou. I'm still not happy about this because I had to make several compensating adjustments that might throw off my Z-axis alignment, which is difficult to measure as I only have a small amount of travel in the Z-axis when my indicator is loaded in the spindle. I will inevitably crash the machine, and at that time I will replace the X-axis. Let's install the work holding and then we can cut this machine's first parts. I have some of my tools preloaded into their holders, but I still need to measure how long each one is. This process will lead to the first part that we're going to machine. Let me explain. On my larger mill, tool lengths can be measured either offline with a height gauge or in the spindle using a tool setter. That's because both methods reference the same thing, the bottom face of the tool holder. The height gauge measures from that surface, and when the tool is installed in the spindle, that same face seats against the spindle nose, which is the reference point for the tool setter. So you're always measuring from a known consistent point. The MASSO control, however, doesn't use that kind of reference system. It doesn't care about the physical dimensions of the tool or holder. Instead, it works with relative positions. It measures how far the spindle moves from a known machine origin to reach the tool setter for each tool. So if I load tool 6, which is a 6mm end mill, and I touch it off, we get a Z offset value of 57.75 millimeters. But that value doesn't represent any physical length of the cutter or holder. It's just some distance the machine had to move to touch off that tool. What matters is that the difference between tools is accurate. So if I load a shorter tool next, in this case a 3mm end mill, before I do that I need to go to Program and MDI, issue an M6 command, tool 3, M6, just so it knows I'm changing tools. We can see here tool 3, tools and offsets, go to tool 3 here. Now this is a manual tool change, so I have to actually press the button to get the drawbar to release the tool. Tool 3, auto 0. The Z offset for this shorter tool is 46.45 millimeters, which means it's about 11.3 millimeters shorter than the last tool. The mill will have to bring this tool down that distance in order to be cutting at the same plane as the last tool. If I keep each cutter in its own dedicated holder, I don't have to retouch it off every time, which is great. But this also means the in-machine tool setter becomes more important than I initially thought. My current touch plate is very basic. It's not spring-loaded nor fixed in the right spot, which both increase the chances of a crash. So the first part I'm going to make is a miniature spring-loaded touch plate that will sit up front between the two vices. I'm sourcing some parts from a larger tool setter that I already had, including a brass cylinder, spring, and bushing. Because the setter will still rely on conductivity, I will need to have a plastic base to isolate it from the rest of the machine. I'm going to start by machining the body out of this 6061 cutoff. I'm using the same speeds and feeds that I used in my last video for the stock spindle. Again, I'm not quite ready to crash the machine with all the effort I put into shimming it, but I promise I'll push the new spindle to the limit in the next video. With the stock material probed and all the necessary tools touched off, I can load the G-code file with my flash drive. Here you can see a visualization of the upcoming tool paths. I will need 4 different tools to complete this operation. When the control's done with one of the cutters, it'll prompt me here to perform a manual tool change and put a different tool in. I resin printed a chip clearing shroud that blows compressed air onto the touch plate before each measurement to prevent incorrect readings. To keep the tool setter electrically isolated, I wrapped Kapton tape around its body and sealed the head of the bolts closest to the table with clear nail polish. I verified the isolation with a multimeter. The tool setter works like a charm, and best of all, it doesn't eat up any of the limited space on the table. That wraps up the build, and while I called this the ultimate compact CNC mill at the start of the video, there are still a few things I'd like to improve and add. The washdown system, for example, helped a lot with chip management, but it still needs some tweaking. I'll extend the spray coverage to reach the back of the mill where chips tend to build up. And of course, the automatic tool changer is the next major feature on the list. That upgrade's coming soon, so if you want to follow along, make sure you're subscribed. If you want to support the channel, using my Oshcut affiliate link is a huge help, especially if you're working on your own CNC projects. And if you reach out to MASSO or Spinogy, let them know Dr. D-Flo sent you. Finally, check my website for the CAD files and bill of materials for this project. And with that, I will catch you in the next one.